All right, guys. Hello, everyone. This is the solution to a sample midterm continued. We come to the third question, which is apply squeeze theorem to prove that the limit of this function is equals to 0. Okay. Before we start, we like to review some of the facts. For example, we understand the range of sine, both sine and cosine is between -1 and 1. And this is true for any real number. This is true for any real number x. Okay, any real number x. In our case, we use this fact, okay? The domain of the function is, x not equal to 0. That's why we mentioned for x not equal to 0, this will be true. And we also needed, when we multiply x to the power 4 on every side, we want to mention that x to the power 4 is positive. Why this is necessary? Because when we multiply a quantity, the same quantity on an inequality, if the number is positive, the inequality sign gets to stay the same. Otherwise, if we multiply by a negative number, we will have to switch directions. When we apply squeeze theorem, okay, you have the index card next to you, right? So you want to quote the theorems. For this question, we basically first, right, we created a squeezed situation from a fact, right? And then we verify the second condition is also true. And so this is to verify the second condition in squeeze theorem. And then we can apply the theorem. So when we apply theorems, we must make sure, and it is easy for the reader to tell, the conditions of the theorems is checked and it applies before we apply the conclusion of the theorem. All right. So that's question number 3. So let's look at number 4. Number 4 is about limits again. In this, there's 3 questions here. Let's look at the first one. The first one was actually covered in one of my recorded lessons for that week. It's titled as limit at infinity. Okay. Notice that we have x approaching negative infinity. Okay. For x approaching negative infinity, hold on, I'm bringing this important note over here. Okay. Because x, okay, I'm bringing it here for illustration. Okay. So what is being tested for this question? There are a couple of things. Number one, what technique we use to solve, limit problems of this sort. The degree of the numerator is 6 divided by 2, because the square root is considered to have a power of half. The denominator's power is also 3. Okay, so the numerator and denominator have the same degree. So we know the common technique. We're going to divide both top and bottom by x raised to the power of 3. So that would be the first step, right? And the second step, we deal with the denominator, right? On the denominator, we basically got x raised to the power of 3 divided into 2, right? So we got 2 over x raised to the power of 3 subtract by x to the power of 3 divided by x to the power of 3. So denominator will get these 2 terms. While x approaching negative infinity, you know, 2 over x raised to the power 3, this has a limit, which is 0, and this is a constant, also has a limit. The question is, if we want to bring x raised to the power 3 inside the square root, we will turn x raised to the power 3 to the x to the power 6. At this moment, we need to take into consideration of these facts. When x is approaching negative infinity, x is negative, we can assume x is negative. If x is negative, its third power is also negative. When we square x raised to the power 3 and then take square root, we will get the absolute value of x raised to the power 3, because x raised to the power 3 is negative, is absolute value, is the opposite of x raised to the power 3. So this brings us to this relationship. Why we do that? Okay, because we want to take x raised to the power 3 inside the root. So we need to create a square root of x raised to the power 6. So eventually we get x raised to the power 3 equals to negative of root x to the power 6. Okay. Similar situations was covered on questions in that week for these questions. Okay, so for the convenience of your study, we have quizzed this question. We have quizzed this question, and we covered that in classroom for it. And of course, we're also going to use this theorem. All right. So anyway, without further ado, let's continue, right? So once we are able to substitute x raised to the power 3 by square root of x raised to the power 6, we found out this relationship. So we will be able to continue. Okay, so I'm going to remove this line, right? So numerator is turning to like this. So x raised to the power 3 is replaced by square root of x raised to the power 6. So now x raised to the power 6 will go inside, right? They're going to be on the same root. And x raised to the power 6 divide into 4 times x raised to the power 6, we get 4. X raised to the power 6 divided into 1, we get 1 over x raised to the power 6. By this time, we can apply limit law. Okay, why? The limit of constants are constants. The limit of 1 over x raised to the power r, which are these, we can apply this theorem. And whether it approaches positive infinity or negative infinity. Okay, so this step is application of limit law. Just remember, limit law can only be used. The individual limits, each individual limits exist. If there's one that does not exist, we cannot use it. We cannot use it. By this time, this limit turns into a 0, and this limit turns into a 0. And the root 4 is a 2. We have 2 negative signs, so we got a positive 2. Okay. So that's one question. Number two. This question is certainly pretty, I would say you've seen it. You've seen it multiple times. Okay, it's been quizzed on. But I'd like to go over this question one more time. From the beginning, we know this is an infinity minus infinity case. But can we do that? The answer is no. Okay? Infinity subtract infinity, you can't do that. You cannot do that. Okay? So what we can do is that we multiply the conjugate. Of course, we understand these techniques, right? And I put the notes here just to emphasize you cannot do infinity subtract infinity, and infinity subtract infinity equal to 0 is wrong, wrong, wrong. Now, for that reason, we do the conjugates, right? We multiply the conjugates. We transform the question. So the question is transformed, okay? And, you know, root minus 3x, root plus 3x, that's a minus b times a plus b, which is a squared minus b squared. So that's how we get this step. Okay, we get the numerator becomes that. Okay, so now we can remove that. Continue, right? On this piece, I wish to review the other facts, which are these. Okay, I'm going to bring it up here. Root of x squared. Wait, root x parentheses squared. You can see these two are alike, but they're very different. They're very different. This one's domain is any real number. Okay, domain is any real number, including positive, negative. Any real number x. And the second one, because we take a root first by order of operation, the domain is x greater than or equal to 0. Excuse me. All right. So we must be very careful about these things. All right. After we got this conjugate, right, a squared minus b squared, the next step, okay, I bring it back to here. All right, so sorry, we're coming back here. You understand all these reasons, right? We did a conjugate, a minus b times a plus b, we get a squared minus b squared. So this piece we get, wait, we don't need this thing, I'm sorry. Okay, so that's just 9x squared plus x minus 9x squared. So when you square 3x squared, you not only need to square x, you also need to square the 3. By this time, we got the numerator to be x. So we get into the situation, this situation is infinity over divided by infinity. Infinity divided by infinity. Right? As x approaching infinity, the top is infinity, denominator infinity. This is infinity over infinity. Does it equals to 1? Can we do that? Of course. I said no. Please don't do that. In the past quizzes, we have a situation like infinity minus infinity, infinity divided by infinity. In either cases, we cannot apply limit law, so don't do it. Okay, so that was the warning. The rest of the steps, you know, we divide by x on top and bottom. And once again, when we get here, right, we want to bring x inside the square root. And because x is positive, right, because x is approaching infinity, so because x is positive, so the square root of x squared, which equals to the absolute value of x, because x is positive, the absolute value of x is the same as x. And that's why we substitute we substitute this x by square root of x squared. So x is the same as square root of x squared when x is positive. Then x squared go inside. We can take x squared, divide into each. We got this piece. And now we can apply limit law. So we can take this limit and inside the constant 1 over x, and 3 is a constant. So by this time, we apply the theorem one more time. So we get 1 over 6. We get 1 over 6. So now we look back on these two situations. One is infinity subtract infinity. Does it equal to 0? No, we don't know, right? Infinity divided by infinity. Does it equal to 1? Of course not, right? So some of these cases we must be very careful about, and also reflect on what it does, imply and reflect. Number three, this is about infinite limit. To answer this question, really we need to understand that we need to be aware of the domain. The domain of this function is x squared minus 9 is larger than 0, while x approaching 3 from larger than 3, x squared minus 9 is approaching 0 from larger than 0. So instead of looking at this function, we look at a comparable situation. That comparable situation is that when x is approaching 0 from larger than 0, right? X approaching 0 from larger than 0, the function's value is approaching negative infinity. So that's how we get the limit. It approaches negative infinity. So it's really a vertical asymptote. All right. So next, let's look at question number 5. Right? Prove that this equation has at least one real root by the intermediate value theorem. Before we do this, there are two things we need to understand. The function was not given, so we have to identify a function so that we can apply intermediate value theorem to that function. Okay? Please have your intermediate value theorem next to you, right? Intermediate value theorem is on a function. And secondly, an interval was not given to us. You have to identify the interval. So let's first identify the function, right? So what is the narrative to identify the function? Well, if there is a root, so we're going to kind of reason from the conclusion backward, right? Obviously, there's going to be a root. Otherwise, they wouldn't be asking us to prove. So if there's a root, and suppose that root is x, then this will be true. If this is true, then cosine x minus x raised to the power 3 will be 0. So that's why we chose this function. Do we have to choose this function? Of course not. I can plus 1. I can choose this other one as a function, right? It's just not equal to 0. It's going to be equal to 1. Why not? But making it equal to 0, right? Finding a solution so that the function will be equal to 0 is like finding the x-intercepts, right? So that sounds like a little easier to deal with, okay? So we have identified this function. Once we have identified the function, you drop the equal to 0 because these two are two different things. Equal to 0 is for some solution, but the function itself, is defined over the entire number line. Secondly, we need to identify the interval. So here we go. We start from simple, right? Substitute by 0 is the easiest. It doesn't mean you're going to have to do 0. You can do, many different. You can do negative pi or negative pi over 2 in negative 3 pi. You can do all of that. But I just try to make it easier for myself. So for f of 0, it's positive, right? For pi, it's negative because the cosine is between -1 to +1, right? So we got the interval, we first got the function, and then we got the interval, and then we're going to start apply. All of these is things I will be thinking about, put on scratch paper. You don't need to show the reader. So what do you show to the reader? Let's go. What you need to show the reader, okay, from the outset, you just tell the reader, I introduce a function like this. It is continuous on the closed interval. Why? Because intermediate value theorem requires the function is continuous on a closed interval. That condition must be satisfied. So we must mention that condition is satisfied. At 0, f of 0 larger than 0, f of pi is less than 0. So we're kind of using the corollary, right? It doesn't matter because you just have to say the capital N. If you use intermediate value theorem, the capital N is 0, right? If you use intermediate value theorem, the capital N is 0, right? If you use the corollary, the capital N is also 0, but capital N was not mentioned, right? All right, so both conditions are satisfied. Then we can apply intermediate value theorem. But when you draw the conclusion, make sure you take the whole of the entire conclusion. So you say there exists a C, and where? C in here, such that f of C equal to 0. But it would be nice if you elaborate on this, because this is the time you want to make a connection to the question itself, right? So f of C exists in here, and that C will cause f of C equals 0, and f of C equals 0 leads to that piece which demonstrates that C is a solution to this equation. Then you say, therefore, this equation has at least one real root by intermediate value theorem. I wish to mention one more time, when we figure out what the function is, in your narrative to prove, you need to understand you should not have equal to 0, which turned out to be a common mistake I saw in the past, okay? Why? Because these two are different. This is the function. We're done with this question, right? I just want to explain what the difference between f of x and f of x equal to 0. F of x is the entire curve from -infinity to +infinity. F of x equals 0 usually is an if statement. It refers to the x-intercept, okay? It refers to when or where, the curve crosses the x-axis, which is to find x-intercept. So these two are very, very different. So once again, to prove by intermediate value theorem, right? You introduce function, don't set it equals to anything, okay? Stuff like that. You can choose different ones, okay? Use different versions of intermediate value theorem, but be careful and make sure you apply the theorem properly and express yourself properly. All right, let's see, do we have more time? I think we're going to make another addition for derivative section. Thank you for watching.